Hello, everybody. Thank you for listening my presentation, Tsunami Hazard Assessment with Consideration of Uncertain Bathymetry. This project was done by scientists from Scripps, from National University of Singapore and Cornell University. So there are many initiatives who have been trying to collect the information about bathymetry of the ocean. For example, GEPCO, ITOPO, etc. This bathymetry information commonly depends on surveys of shipboard surveys and also bathymetry models in the oceans. So far, we have mapped around 11% of the bathymetry using shipboard instrument. For the remaining 89%, we need to derive models based on indirect data measuring the bathymetry. This is the case of the gravity anomalies measured by satellite altimetry data, which can be related with the bathymetry. This method is very powerful and actually allow us to get 100% of coverage of the bathymetry of the oceans. However, the method has a problem related with the upward continuation, which doesn't allow us to get scales smaller than 10 kilometers. Therefore, we need to understand what are the errors and the uncertainty related with the lack of this high wave number content in the bathymetry models based on altimetry data. So the question is, can we recover the information of the high wave number content of the bathymetry? Well, the answer is no. There is no way or deterministic way in which we can obtain that high wave number content. However, we can describe statistically the behavior of the high wave number content, and therefore we can adopt a stochastic approach in order to model or to generate synthetic bathymetry. This is how, from the 70s and the 60s, we developed the idea of fractal behavior, in which we can relate the amplitude or the size of small scale of the bathymetry with the longer scale. Using this fractal behavior also, Dr. John Goff, for many years, have developed new tools based on stochastic approaches in order to generate synthetic bathymetry for high wave number content. So in this work, what we are doing is trying to extend the work of Dr. Goff and try to generate a stochastic tool in order to understand the uncertainty of the altimetry bathymetry models and a method to generate synthetic bathymetry to supply that high wave number content we are missing in the altimetry-based bathymetry models. So in this study, we are following a three-step approach in which first we have to define the probability properties of this high wave number content of bathymetry, which constitute the error of altimetry models. Then we have to devise or design a method in which we can generate samples of synthetic high wave number content of bathymetry. And third, we need a method in which we can propagate bathymetry's uncertainties to any physical process which is modeled using the bathymetry as input. In this case, we are working with a tsunami hazard assessment. Okay, in order to understand the probability properties of the high wave number content, which constitute the error of the altimetry bathymetry models, we collect 15 regions in which we have multi-beam surveys. These multi-beam surveys have a very high resolution, and therefore is assuming this study to be the real bathymetry or the true bathymetry. So we compare these multi-beam surveys, which are shown in the bottom panels. We compare it with the altimetry-predicted bathymetry model. And we obtain the error, and those errors will be analyzed statistically. So the first thing we have to identify is that if we compare the multi-beam survey with the altimetry model, we can observe that the altimetry-based model have a lack of high wave number content, which is basically the idea we have been mentioning in the previous slides. and therefore is a blurry version of the true bathymetry. This blurry version is related with this lack of high wave number content in the power spectral density. Here we have a transect of the power spectral density in the log-log plot, in which we have wavelengths or wave number in terms of the power spectral density. And what we can observe for fractal behavior is that we have a constant power decay law, which is related with this self-similarity of fractal behavior. And using this information from the bottom part, from the longer scales, we will try to describe or try to fill with synthetic bathymetry that, that part of the spectrum which is missed. So we did that, and what we discovered is that using the 15 samples from the 15 regions in which we have multi-beam data, we could get some black dots which are related with the power spectral density of the error, which is equal to the high wave number content. And using a very simple model, which is the von Karman function, we fitted a curve, a global curve, in order to fit those empirical power spectral density. So therefore, we can model the covariance or the power spectral density, which are related, with a model in order to build a random field model. Also, what we did was to do an analysis of the variance of the error, and what we discovered is that we have different values in different regions. However, what we discovered also is that using information of the total variance of the satellite altimetry bathymetry model, we can use that information in order to get a scaling law in which we can relate information of the altimetry model with the actual variance of the error we are obtaining in each region of the world. And therefore, we can get all the second moment properties for the bathymetry error in any region of the world. Also, what we analyzed was the marginal distribution of this error. And what we discovered is that Gaussian actually is not a well representation of the marginal distribution of the error, but we discovered that other functions like the Laplacian distribution, which has longer tails and heavier tails, can represent in a better way the distribution we have observed in the empirical analysis of the errors in these different 15 regions. Therefore, we also propose a model for the marginal distribution based on a Laplacian distribution, which is the green line. Finally, once we have the probability properties, we need to specify what are the sample generation method. And for the sample generation method, we use a conditional random field in which the uncertainties specify as 0 in places where we have shipboard measurements, and equal to the uncertainty model we calibrated before in places where we don't have measurements. So as an application case, we are conducting a tsunami hazard assessment with consideration of uncertain bathymetry. And for this, we use an illustration case in northern Chile due to a tsunami generated by the 2014 earthquake. So what we are doing in this illustration case is, first of all, take some bathymetry model, in this specific case, the bathymetry model of SRTM 15+. We will include uncertainty in places where we have a prediction from satellite altimetry data, and we will complement the bathymetry model with samples of high wave number content, and finally we will solve and we will obtain different samples of the bathymetry containing all the content in the high wave number content and the long wavelength content. As a result, here you can see, after to run a Monte Carlo simulation, some statistic about the tsunami response. In this specific case, the maximum tsunami elevation, where here in the top panels I show the mean, and in the lower panel I show the variance. And you can observe that two main conclusions. First of all, the uncertainty is very high in the shallow area, in which tsunami waves become shorter wavelength, and also interact with an uncertainty which is comparable to the water depth. In deeper regions where the uncertainty is much smaller than the mean water depth, we can see that the uncertainty of the tsunami is much smaller. Also, to gain more insight, we can observe here also the time histories of the tsunami elevation in different 12 locations along Chile. And we can always observe that the leading wave is actually not affected by the bathymetry uncertainty, which is good news, for example, for early warning systems. However, for the second and trailing waves, we can observe a very strong sensitivity to the bathymetry uncertainty. So as a conclusion, we have two relevant findings from this study. First, we can create an uncertainty model which can model the error or the uncertainty of the altimetry bathymetry model, which can serve as a first order approximation of these errors or uncertainty. And second, we observe that leading tsunami waves are not severely affected by the bathymetry uncertainties in Chile. In the future, also, we are planning to do more work. First of all, we would like to improve the random field model, which actually is the engine who generate this synthetic high wave number content of the bathymetry. We would like to include a more sophisticated model, which can include local properties of the bathymetry in different regions. Also trying to deal with the heterogeneity of the random field and the anisotropy, which are very important in some locations. And finally, we want to test also the tsunami hazard assessment in other settings. For example, it's very important to see what is going on when you have a tsunami wave propagating over a very long continental shelf. We want to see if that the leading wave is still not severely affected by the bathymetry uncertainty. And for that, we will conduct a tsunami hazard assessment again in the South China Sea, specifically in Hong Kong, due to earthquakes generated in the Manila subduction zone. So thank you very much. And here is the link of the paper which tell all this methodology and the study. Thank you very much.